morning, class. It's Monday morning. Welcome to digital class with Mr. Talley. Here we go. Okay, so we're doing some things differently. You're not in class normally. You're at your house. Let me walk you around the classroom. Okay, here's the whiteboard. Welcome to my class. There's some things that you're gonna need to know about science class. One, every Monday at 11 a.m., I'm gonna open up a Google Hangout for us to answer any questions that we have about what's going on in science. Some other things that you need to be aware of. I need you to familiarize yourselves with the Google site that I made that's linked to Google Classroom. So I put a bunch of stuff on Google Classroom, and that's the main place I'll be communicating with you. But all the resources are on Google Sites. So if for some reason you gotta find a video or you gotta find an assignment, they're all on Google Sites. It's actually really cool. I spent a lot of time working on it. The other thing that you might be interested in, you need to get on Remind. I've never used it before, but I'm trying to be more connected since we're not face to face anymore. So check out Remind. I think you text 81010. I also put that on Google Classroom for you. Okay, it's Monday morning. We got some assignments coming up today. I want to see your Unit 5 study guide. I know it's in your binder, but if for some reason it's gone, I've linked it on Google Classroom for you. I've linked the key on there. So here's what I want. For today in Google Classroom, you need to submit either a picture of the one that's in your binder, Unit 5 study guide that's in your binder front and back, or a copy of the digital one that you have filled out. Okay, so you need to turn in one of those two options. Either one works for me. Today in class, we're gonna go over the key because tomorrow is your Chapter 5 test. We're still doing that test. It's gonna be online tomorrow, on Tuesday morning. Tomorrow, I will give you the code. You'll have all day until midnight to access and complete it. Every assignment ever that we're ever gonna do online, I will post it at 8 o'clock in the morning and it'll be due by midnight, unless it carries over. Like, we're doing notes on Thursday and they're gonna be due on Friday because we're gonna finish them on Friday, okay? But you'll always have till midnight to turn something in. Although you should be going to bed at 8:30, but you have till midnight. Okay, so that's it on the board. Whoops. Let's get started with the study guide. Here we go. Let's get blam. Okay, so I'm just gonna go over some of them. They're on your key, right? But I'm gonna try and explain some. So that what you really need to know right at the beginning, there's the 5 different types of chemical reactions. The first type of chemical reaction is combination, okay? And you're gonna see some kind of reaction like something like Mg plus O2 is gonna react and combine. It's two single things. Like it's literally one element of magnesium and one type of element, oxygen. They're gonna combine together and form MgO. And I know you're wondering, where did that 2 go, right? We'll talk about that in part 2 of the study guide. But I just want you to see that we've got some kind of, here, let me use different colors. We've got some kind of A compound and some kind of B compound, and they're combining together and you get A, B in one chemical compound, okay? So this is combination. You take 2 individual things and you create one ingredient. It's the only type of chemical reaction where you start out with 2 ingredients, 2 reactants, and you form only one product, okay? So that's gonna be combination, okay? Oh my gosh. Oh, the second type of reaction that you're gonna be looking at is decomposition, okay? A decomposition reaction is the exact opposite of a combination reaction. It's literally flipped. So we'll take our example will be mercury oxide is going to react or decompose in this example and form mercury and oxygen gas. okay? And so what you're doing is you're taking one reactant and it's going to decompose and break apart into two different products or more, could be more. And so this is the only time you see something with only one reactant, and it's going to break apart into more reactants. And if we look at the generic formula in our key, and you're trying to tell me what type of reaction's going on, you've got some kind of A and B combined together, and it's going to react and it's going to form some kind of compound A and some compound B, right? We've got AB here, mercury's the A, oxygen's the B. They've been separated, okay? Now they're individual things. The oxygen gas is going to come out of solution. We'll light it on fire. It will be fine. Okay, let's look at the third type of reaction. Okay. The third type of reaction on our cheat sheet, or on our study guide, is the single replacement. Okay, and I'm going to give you some tips to be able to identify this, but let's just write down an example real quick. Let's do iron oxide plus something that's more reactive like sodium. These two compounds are going to react, and you're going to end up with, right, we're going to take this metal and this metal, or this cation, they're both cations, metals are cations, they're going to switch places, okay? So this guy is going to switch places with iron, and you're going to end up with sodium hydroxide plus just some solid iron, okay? And so the reason why we call this a single replacement is because there's only one replacement going on, okay? Just one replacement, just the two metals are switching places. One way to be able to identify this that separates it from a double replacement is that the sodium is by itself. It doesn't have another anion. Iron has a hydroxide anion, but sodium, it's by itself. It doesn't have another anion. And then over here, the iron doesn't have an anion. It's alone. It's single. It's by itself. That's one way that I think about when I'm identifying. And then I'll show you what does it look like with the general equation. We've got some, right, the iron is the A, the hydroxide here is B, and the sodium is going to be C. Right now, A and B are chemically combined in a compound, but A and C are going to switch places. So now we're going to end up with CB plus A by itself. Okay, and you can see A and C switch places. This is a single replacement reaction. You're going to need to identify these on the test tomorrow, so make sure you're familiar with this. Okay, we're going to do the fourth type of chemical reaction, which is the double replacement. Some people say double displacement, double replacement, same thing. Okay, so let's come up with an example. Let's do something like calcium carbonate and sodium chloride. Oh, I didn't save it for. Okay, this is gonna get messy. Okay, calcium carbonate plus sodium chloride. It's gonna react in a double replacement reaction. What's gonna happen is the calcium and the sodium are gonna switch places, okay? The reason it's double replacement is because the calcium is switching partners and sodium is switching partners. They both are swapping partners. And the other one of them was already a single, but now they're both switching partners. So what we're gonna end up with is calcium and sodium are gonna have new partners. Don't put the calcium and the sodium together, because these are both metal cations. They both have a positive charge. They don't want to be bonded together. They don't have any attraction to each other. But the anions are attracted to the cation. So we're going to switch those partners. So we'll end up with something like sodium. We're actually going to get Na2CO3 plus CaCl2. And that's because this guy's got, I don't know, -2. And this guy's got +2. This guy's got +1, -1. But we're going to go over that in the next part. I'm getting ahead of myself. Okay, in a double replacement reaction, I'm going to write down, do I have another color? Yeah. We'll look at the generic formula as well. So we've got, we'll say calcium's A, carbonate's going to be B, so we have AB. We've got sodium C, and what color are we have left? Red. This is way harder than I thought it was going to be. Okay. And so AB, CD. Those are the compounds we have right now. When we switch them around, we end up with, here's D over here. Blue was B. Purple was A, and now A is over here. And green, C. Okay, so now instead of AB, we have CD. Instead of CD, we have AD. The two cations, the two metals, swap places. That's a double replacement reaction. Okay, so one way I see that as different than a single replacement is that both of them, both reactants have partners. In the last example, if you rewind, one of the reactants was a loner. Okay, but now they both have partners. They're both swapping partners. Okay. Okay, let's look at the final reaction type. It's definitely the most fun, but sometimes this one can be the trickiest. Okay, so this one's going to be combustion. Combustion. It's fun because it's exploding, it's releasing energy in the form of light and heat, but it is confusing because sometimes it's a hydrocarbon, sometimes it's not. So let's just write down what we're looking at. So we're going to have some hydrocarbon, carbon and hydrogen. Hydrocarbon just means a compound that has carbons and has hydrogens. And I'm going to label it CXHY. So some random number of carbons and some random number of hydrogens. This is one of our reactants. It's always going to react with oxygen. Okay? This is an always. Always going to react with oxygen. When it reacts, and this is only when you have a hydrocarbon, something with C and something with H, every time you're going to produce CO2 plus H2O. You'll get some number of carbon dioxide molecules and some number of water molecules. Okay? This is combustion. Whenever you see one of the reactants is oxygen, you're going to go, oh, it's probably combustion. Okay? You'll see oxygen, you'll go, combustion, boom, I know it. For the most part, I'm always going to give you a hydrocarbon as the other reactant, but it can be something like something we did earlier, Mg plus O2 is going to react. And we did this in the lab, remember? We took the magnesium ribbon, we lit it on fire in the Bunsen burner. That's because we were combining it with oxygen, and it produced MgO. So it was combustion in that it's reacting with oxygen, but we couldn't produce carbon dioxide or water because we didn't start with any carbon and we didn't start with any hydrogen. So we could only produce MgO. Okay, so that's kind of a tricky situation. But for the most part, combustion is usually some hydrocarbon, some C2, H4, whatever, plus O2, and it's going to react and form CO2 and water. Okay, so let's go on to part number 2. We're going to be looking at balancing and identifying types of reactions. I'm just going to go through a few of them that I think are tricky, and all of the answers are on Google Classroom for you to check out. So I'm just going to do a few. I'm actually going to do the first one even though it's not super tricky. So it tells us we have HgO plus, no, not plus, reacts to form Hg plus O2. Okay. So, if I look here, well, let's actually do the reactant product table chart. Okay. We've got mercury and we've got oxygen. On the left side, on our reactant side, we have one of those. On our product side, we have one of those as well. On our reactant side, we have one oxygen, and on our product side, we have two oxygens. So we go, oh no, we're unbalanced. We thought we were gonna make it, but we didn't. Okay, we gotta figure out how to balance this. The oxygen is not balanced. So to make this oxygen and this oxygen the same, I'm just gonna multiply the left by 2, because if I multiply 2 times 1, I end up with 2. So I'll put a 2 coefficient here. So that makes my oxygens equivalent. But that messes up my mercury count, and I get 2 because the 2 distributes to both of the elements in the compound. So I need to make sure mercury is balanced on both sides. So I'll put a 2 here as well, because 1 times 2 equals 2. And then we're happy, and we balanced it. Great job, everyone. If it's blank, that means it's 1. Okay, just so you know, if it's blank, it's not a 0, it's a 1. Cool. Any questions? No? Okay, we'll move on. All right. The next one that I want to do with everyone is number 5. Number 5 is tricky, and I like it. So, number 5. This is going to be a great question. We've got C3H8. C3H8. We're looking at a classic combustion reaction. I can already tell because it's a hydrocarbon, right? Carbons and hydrogens. And guess what the next reaction is? Yeah, good job. You guessed it, Braden. It's oxygen. All right. It's going to produce, well, it always produces CO2 and water. Okay, but it's not balanced. And we're looking at a combustion reaction, so most of the time, they're really tricky. Let's get our reactant product table up. We've got carbons as one of the chemical species, hydrogens, and oxygens. Nothing else. On our reactant side, we've got 3 carbons, but only 1 carbon on the product side. Hydrogens, we've got 8 on the reactant side, and only 2 on the product side. Oxygens, we've got 2 on the reactant side, and 2 on... Just kidding! You thought I messed up. There's a third one right here. Don't forget to count all the oxygens. That's 3. Okay, you're looking at that. None of them are balanced. That stinks. What we want to do is save oxygen for last, because oxygen is by itself. So if we put a coefficient there, it will only mess up the oxygen count. It won't mess up carbons or hydrogen. So we want to save this guy for last. So let's balance carbon or hydrogen next. Now, I don't like odd numbers, but this one's so easy. So what I'm going to do is I'm going to multiply this hydrogen. I'm going to multiply it by 4 so that I get 8, because I have 8 here. So I'm going to put a 4 next to my hydrogen, and we got an 8. That's also going to mess up my oxygen count. So we need to recount the oxygen. We have 2 here and 4 there. Yes, that gets us 6. Okay? So we're not going to mess with the oxygens yet. We're going to mess with the carbons right now. Carbon, right, we need to balance that, so we're going to multiply that by 3 to get 3, so that we have 3 on both sides. We should come up with a better way to do that. We'll put the 3 there, and that's going to mess up my oxygen count again. I'm going to have 4 here and 6 there, so that gets me to 10. Okay? And then the only thing we have left to balance is this oxygen. We'll put a 5 here, because 5 times 2 equals 10. And so we are happy and balanced. Good job, everyone. Okay. Let's do the next one. The next one we're going to do together is number 7. Number 7. We've got potassium plus water. Ooh, this would be a fun reaction. Potassium plus water is going to give us potassium hydroxide plus everyone's favorite, hydrogen gas. Okay? This would be super fun. Remember when we threw the sodium in the water and exploded all over the place? Pretty much the same thing. Okay, let's do the reactant and product table chart. We've got potassium, we've got hydrogen, we've got oxygen. Okay, potassium, we've got 1 on both sides. Hydrogens, we've got 2 for our reactants and 3 for our products. Oxygens, we've got 1 reactant, 1 product. Okay, so we gotta balance this guy. What are we gonna do? Well, we wanna leave potassium and hydrogen till the end, so let's deal with oxygen first. We don't need to, so now you can just pick whatever you want. Well, never mind, there's only hydrogen left. So, because everything's balanced, 2-3 switch looks like maybe, but no, we can't do that because there's hydrogen in 2 places. So that's not gonna work out. So I'm thinking, oh my gosh, what the heck am I gonna do? What I'm gonna do next is actually, because I don't like that this is odd, it's easier to deal when it's even. So I'm just gonna multiply this by 2. It's gonna mess up everything, but it's all gonna work out in the end. So this is gonna change my hydrogen count to 4. It's going to change my potassiums to 2. It's going to change my my oxygens to 2 as well. Okay, so now I know I need to multiply potassium on the left by 2, and that gives me 2. And I need to multiply oxygen on the left by 2. And I also need to multiply hydrogen on the left by 2, which actually it works out perfectly because I can multiply them together by 2 and I get 4 and 2. Boom! Wow, great job everyone. Okay. We're going to do one more together, and if this is confusing for you, then we can do the office hours at 11 today. Okay? So don't be late if you want to be a part of that. Okay, the last one we're going to do is number 8 because it's another combustion one and it could be tricky. So we're doing number 8. We've got C2H2 plus, what is it? O2? Yeah, good job, Kevin. All right. And that's going to react and form CO2 plus H2O. Okay. So what's going to happen? We got to balance this. Let's do the reactant and product table chart. Reactants, products. We've got carbons, hydrogens, and oxygens. Let's count them up. Okay. On the left, we've got 2 carbons, 1 carbon. For hydrogens, we've got 2, and we've got 2 hydrogens for our products right there. For oxygens, we've got 2 on the left, and on our product side, we have 3. Okay. Remember, we want to save oxygens to the end because oxygen's by itself. So we don't want to mess with that right now. Let's mess with carbons first. So carbon, we need 2 more, right? We need to multiply this guy by 2. So I'm going to put a coefficient of 2 right there. That's going to give me 2 carbons. But it's going to change my oxygen count to 5. This gets us to the old 5-2 switcheroony. So, when you get to a place where everything is balanced except the oxygen has some odd number and a 2, there's a special tricky move you do. And what you do is you take the 5 and you're going to multiply that by the oxygen on the other side, which is going to give you 10. Okay? And now, the next part of the step, next part of the move, is you change all the coefficients except for that 5. You double them. So this is a 1, we'll change it to 2. Ignore the 5. This one's a 2, so we're going to change it to 4. This one's a 1, so we're going to change it to 2. And now, when we count them all up, everything has doubled except for that 10. So we end up with 4, 4 here. We end up with 4, 4, and 10. Boom, we're amazing. Great job. Okay, so let's erase that. Okay, let's move on to part 3. I'm just gonna do the first one because I wanna explain some principles, and I have all the answers for you on the answer key. Okay, so it says, classify the following chemical reaction. Okay, so you gotta tell me, is it combination, decomp, single, double, or combustion? And then it says, be sure that all reactions are balanced, and compounds are labeled aqueous, that's the AQ, parentheses AQ, solid, liquid, or gas. Okay, so the question says, solid sodium and copper sulfate react to form sodium sulfate and solid copper. Let's start at the first ingredient. It says solid sodium. Okay, so Na, solid. I got the element symbol, and it says solid. And then it says that's added to, so I'll put a little plus, added to copper 2 sulfate. Okay, and the Roman numeral 2 tells us what the charge on copper is. Okay, so I know copper has a 2 plus charge, and sulfate, SO4, if we look at our cheat sheet, has a -2 charge. So that means when I write the formula, I only need 1 copper and 1 sulfate, because a +2 and a -2 together equals 0, and that's the goal, right? When we're writing an ionic compound, we're trying to make sure the compound is neutral, meaning it has a 0 charge. And so this guy works out. And it says that they react to form sodium sulfate. And I gotta make sure the charges are right. So I know that sodium, because it's in column 1A, has a +1 charge. And sulfate still has a -2 charge from our cheat sheet. And if I add these together, I do not get 0. Oh no. What am I gonna do? I need to multiply this by 2 so that I have a +2 and a -2 that cancel each other out. And that's why I put the subscript 2 after sodium, okay? It doesn't come from over here, it comes from the charges, okay? We don't look at any of the subscripts over here, we look at the charges, and that's how we figure it out. And then there's one more product, and that's gonna be the solid copper. And so we'll have copper solid. Oh. And to tell me if either of these are aqueous or solid, you'd have to look at your cheat sheet. And you'd have to check the solubility tables. But I'm gonna tell you right now, they're both aqueous. And I know that, well, I know you can't add 2 solids together and have a reaction. So I know this one's gonna be aqueous. And I know this one's gonna be aqueous because sodium with anything is aqueous. So that's what I'm going with. But you can check your cheat sheet to make sure I'm right. Okay, we gotta balance this guy. So let's do our reactant product table. Okay, reactants on the left, products on the right. We have sodium, we have copper, and we have sulfate. I'm treating sulfate as one compound, one chunk, because we have sulfate on the left and sulfate on the right, and they're not split up or messed up, so it's acting like one element. We have 1 sodium here, 1 copper, and 1 sulfate. And on the right side, we have 2 sodiums, 1 copper, and 1 sulfate. So all we need to do is balance the sodiums, which means I need to multiply the sodium on the left by 2, so that we get 2 on each side. So I put a 2 here, and change my count to 2. And bada bing, bada boom, it's all done. We did it. Great job, everyone. Oh wait, we figured out one thing. We didn't identify the reaction type. The reaction type. Okay, well, let's think about it. We've got a single element by itself combining or reacting with an ionic compound, and that single element replaced that single metal replaced the other metal, and now that element that got replaced is now single. So what do you think it's gonna be called? It's called single replacement. Yeah, it's single replacement. amazing. Okay. All right, so you're gonna do the same thing for the next question in part 3. I have the answers there for you, but remember, the only way you figure out what the formula is you look at the charges, and they're all on your cheat sheet. Every element, every polyatomic ion, it's on the cheat sheet. You just gotta look at it. I gave it to you, so you could cheat. Okay, we're looking at part number 4. I'm just gonna do the first one with you, and then the same principles will apply. So it says, predict the products, including the state of matter, so you gotta tell me if it's aqueous or solid, and balance the equations. So the first one says, we have Pb, so lead nitrate, NO3, and it's lead nitrate, but it's NO3 too, and that's gonna be aqueous. And we're gonna combine that with calcium hydroxide, so CaOH2, and that's aqueous, okay? Uh-oh, I might have to use, it's not gonna get pretty, okay? I'll try and write better. Okay, so we need to predict the products. So I need to figure out what type of reaction this is. Well, there's only one type of reaction where we have 2 compounds that each have a partner, 2 buddies, right? The only type of reaction that is a double replacement reaction. So I know this is a double replacement reaction, and if I know that, I know what the products are gonna be. I know that this metal and this metal are gonna double switch partners. They're gonna have new partners at the end. And so calcium is gonna go and hang out with nitrate, and lead is gonna go hang out with hydroxide. We have to figure out what are the charges for everything, and that way we can identify what's going on. I know that nitrate, from my cheat sheet, has a -1 charge, and if there's 2 -1s, then I know lead has a +2 charge, because we want them to be neutral, we want them to be 0. So there's 2 -1s, that means lead has to balance that out, has to be a +2. Hydroxide has a -1 charge, and calcium has a +2 charge. There's 2 hydroxides, 2 -1s, and 1 +2. That's going to cancel out, be neutral as well. Okay, so we're gonna switch calcium and lead, so we'll end up with lead, and lead's gonna be combined with hydroxide. And because lead's a +2, hydroxide is -1, I'm gonna need 2 hydroxides again. And so let's check our cheat sheet real quick, or let's check our solubility chart. We look for the hydroxides in the left column. We scan across. Oh, what's that say? Oh, this is gonna be insoluble, meaning it's a solid. It does not dissolve, it's a solid, it's insoluble. Lead hydroxide is a solid, it's insoluble. The other product that we have is gonna be calcium combined with nitrate, and because calcium is +2 and nitrate is -1, I need 2 nitrates. I didn't write that very good. Okay. And now we gotta look at our cheat sheet. I look at my cheat sheet. Nitrates, always soluble no matter what. So that means this is going to be aqueous. Sorry, that's hard to read. Okay. We did it. You gotta look at the charges to be able to predict the products. Once you have the products, then you can use your solubility chart to determine if it's a solid or aqueous. Okay, let me give you a solid equals insoluble, and aqueous, aqueous equals soluble. Okay, these are from your solubility chart, and this is what you need to write next to each compound. Okay, let's look at where it's the next set in part 4. It says, predict the products of each reaction, use the metal activity series to determine if the reaction would actually occur. Okay, so we're gonna be able to determine if this reaction will actually happen or not. Okay, so let's just do the first one at the top. We've got calcium plus, and it's gonna be reacting with MgSO4. Okay. And calcium is going to be a solid. So we'll write the little S. MgSO4, aqueous. Okay, they're going to react together. They're only going to react if calcium is more reactive than magnesium and can kick magnesium out. So we'll look at our reactivity series. Is calcium higher than magnesium on the chart? Yep, it is. Okay, so we know this reaction is going to happen. Reaction will occur. Okay, so now we need to figure out what type of reaction is this. That way we can predict the products. Well, calcium's a single element by itself. And I know that this compound, there's a metal cation and an anion. So if there's a single element and then a metal cation and an anion combined, this has to be, what was that? Yes, single replacement reaction. So calcium is going to replace the magnesium. You're not going to combine the two metals together because they're not attracted to each other. You're going to combine the calcium metal with the sulfate anion. So we'll end up with calcium sulfate, CaSO4. And because sulfate has a -2 and calcium has a +2, we just need one of each. So when I write the formula, I don't need any extra subscripts anywhere. And we'll also combine, or maybe not combine, we'll add or have magnesium solid. Okay, we need to determine, is this guy going to be aqueous or solid? Is it going to be insoluble or soluble? Well, we look at our cheat sheet, we look down the sulfate list, and we go across and we go, okay, well, it's going to be aqueous. That means it was soluble. Okay. You're going to be doing that for the next 3. Make sure this metal, if the reaction will occur, this metal is higher up at the top of the list than this metal. This metal needs to be down at the bottom of the list. Or as long as one is higher, this one is higher, and this one is lower, the reaction will happen. Okay? Great. All right, part number V, part number 5. It says, what are some signs of a chemical reaction? You need to know 4 signs that indicate a chemical reaction has occurred. And this is going to be straight from your toolbox of terms. Okay? So the 4 signs a chemical reaction has occurred. Okay, number 1. What was that? Yeah. Okay, bubbles. That's one. If there's bubbles or gas being emitted, some kind of steam, a chemical reaction is probably going on. The next one is going to be a light emitted. Light. Okay, if light's emitting, you're seeing some kind of fire, right? This can also be heat emitted. So you could say number 2 is energy, light, or heat. The third one we're going to do is a color change. Okay, if we see a color change, then we know a chemical reaction has happened. If the color is completely different, or even any kind of color change, a chemical reaction has happened. And the fourth one is a precipitate. If we added 2 liquids together and we formed a solid, we know a chemical reaction has happened. These are the 4 signs of a chemical reaction. Let's do number 5 real quick. Here we go. Number 6. Part number 6 says, state 2 examples of a physical change and 2 examples of a chemical change. Okay, so we've got physical, we've got chemical. You can write anything you want as long as it's a chemical and a physical change. I'm going to write, for physical change, melting. I'm going to write freezing. boiling. I know you only need 2, but boiling. What was the other one I wanted to write? It was dissolving. Like when you dissolve salt and water, it's still salt. Remember, we just boiled the water out and there's salt left. We did that in the lab. Some chemical reactions. You could do baking soda and vinegar. You might have done that before, right? It releases a bunch of bubbles. That's one of the signs of chemical reaction. Another one, baking cookies. Among other things, you're going to see a color change, right? We're forming new chemical compounds. You'll see a different color. You'll smell some good things. And eventually, you'll taste some good things when they come out of the oven and cool down. So those are going to be our answers. You can add other chemical reactions if you want, or you can take mine. And then finally, part 7 is a little tricky. I wanted you to think about it, right? Because I want you to think about what's going on. And so I asked, how can you differentiate between the presence of oxygen, hydrogen, and carbon dioxide gas? And in all the labs, we have created oxygen gas or hydrogen gas or carbon dioxide gas, and we did different things with them. And so I'm going to, for all of them, I'm going to take a wooden stick, light it on fire, and we did that in the last lab, right? We took the wooden stick and we put it in CO2. What happened when we put the flame in CO2? The flame went out. The flame went out, right? Because it had no oxygen, it was only carbon dioxide, the flame couldn't burn. So now we need to figure out what's going to happen with oxygen gas and hydrogen gas. And remember, the last time we were in class together, I took calcium, mixed it with water, and we filled the balloon up with hydrogen gas. What happened was, pop, it all burst in an instant. And so what happens is the flame is going to pop. And it's all going to ignite all at once. But if we have oxygen, the flame burns brighter. And that's because it has more fuel, more energy to do combustion reactions. And that's what we're looking at with oxygen is combustion reaction. So it's going to burn a brighter flame. So those are the 3 things. If you wrote something else, you talked about, you didn't talk about a wooden flint on fire. If you talked about, if you breathed them in, what would happen or something else, or density, that's cool. And I'll take that as well. But that's going to be everything you need for your study guide. Turn that in by midnight tonight. You're awesome. And hopefully I'll get to see you in class real soon. See you tomorrow. Make good choices.